And behavior, there's quite a bit to cover in this, so this is going to be one of the longer videos, but you're only going to have to watch it. You're going to have 2 days worth of assignments on this, so you only have to watch it today. Tomorrow you get a break. So continuity, the first part of it, is this idea of, well, let's start, well, I need to be able to draw. For continuity, let's deal with that first. Then we'll get to end behavior after we deal with the different facets of continuity. Continuity is a simple concept. It's the idea that something being continuous, it goes on and on without break, right? And that's what we mean when we talk about continuity of a function. We want to have a graph that we can draw from left to right, from negative infinity to positive infinity, for example. If we just have a graph and we're going, when we talk about functions, we generally talk about functions behavior going from negative infinity to positive infinity, or left to right. So if I have a graph and I'm drawing it, and I can go from one end to the other, from negative infinity to positive infinity, and not pick up my pencil while I'm drawing it, then it's continuous. All right. If there's a break in any way, if I have to pick up my pencil to start again, we have what's called a discontinuity. All right, so just another word to know. There are different types of discontinuities. All right, we're going to work on recognizing some basic discontinuities, and then we're going to look at how we prove at any point whether a function is discontinuous or not. All right, so let's look at some basic types of discontinuities. All right, so discontinuities. All right, what do we have? First one would be an infinite discontinuity. An infinite discontinuity occurs when we have an asymptote, essentially. All right, just let's look at an example. I think it's easier to see when you actually see it. You're familiar with the function f of x equals 1 over x. We've brought that up a few times this year. That has a graph, just to give you a quick sketch, that does this kind of thing, right? And we know it has asymptotic behavior at x equals 0. There's an asymptote going down this way and this way. And that occurs because it never gets all the way as a y value to 0. And also at 0, as we get closer and closer to 0 from the left, it gets further and further to negative, towards negative infinity. As we look and approach from the right, it goes closer and closer to positive infinity. So when we look at this, we see that if I were drawing this, if I were trying to trace this from left to right, here I've got to stop, pick up my pencil, go across that discontinuity, and then start again. And I can then go towards positive infinity forever. So we say this has a discontinuity, an infinite discontinuity at x equals 0, because at 0 we get an undefined value, so we had to pick up our pencil to go across that gap. All right, so that is an infinite discontinuity. Let's do the next type. All right, if we look at the next type that we're going to discuss, that would be a jump discontinuity. All right, when we have a jump discontinuity, it's just what it sounds like, and it's again a function type that we often see it in that you're familiar with. Something like this, we have x squared plus 1 when x is less than 0, x when x is greater than or equal to 0. Again, if I look at this graph and give a quick sketch of it, if we're at 0, 0 plus 1, 0 squared plus 1 is 1. So at 0, I'm at 1 with an open circle. Let's do this in another color. And then if I go in the domain of x less than 0, I go to 1, I'd get 1 squared plus 1, that's 2. So I'd have a point up here, and this has that curve like a parabola because it is half the parabola. It comes, as it approaches 0 from the left, it goes towards 1. Now, from the right, starting at 0, I plug in 0, I get 0. So I have a closed circle here, and then at 1, going into its domain, 1, I'd have 1. So at 1, I'd be at 1, and we'd have this graph going out this way. So what happens to create a discontinuity here? Well, think about it. If I'm tracing from left to right, I get really close to 1 as I get really close to 0 in the x value. So as x approaches 0 from the left, this value approaches 1. Then what happens is as soon as I hit 0, it jumps down to 0. And then as x approaches 0 from the right, this whole value of the function is approaching 0. They're approaching different values, right? When they're approaching different values from the left and from the right, it makes you jump. All right, so that is a jump discontinuity at x equals 0 again in this case. All right, so next one and last one that we're going to deal with is something that we in general call a point discontinuity. These are all about discussing continuity at a point, but when we talk about a point discontinuity, well, I left out a whole syllable there. All right, let's try that again. Discontinuity, there we go. All right, sorry about that. So point discontinuity we also know as a whole. You've dealt with these in the past. This would be something like f of x equals, say, x plus 1 over, or times x plus 2 over x plus 1. We know, if you remember, we know this graph, if I sketch it, will look like, because the x plus 1, everything I put in here, if I put x equals 1, I would have 2 plus times 3 over 2. So the 2's would cancel and leave me just the x plus 2 value. So this thing is going to look like x plus 2. And if you doubt that, you can go ahead, whoa, I missed the 2. You can go ahead and graph this. And if we were to graph this, let me turn on my calculator. This is, I already prepped it, x plus 1 times x plus 2 over, let me see, let me just move right so you can see it, divided by x plus 1. And when we graph that, we get this graph. It looks like a line. But if I go into my table values and I look at -1, where we know, like if I put -1 in here, what happens? -1 plus 1, 0. So I know at -1, it doesn't have a value, and that tells me it in the table. So what happens there? Well, it's a hole, because as I'm going across here, as I'm going from left to right, as I'm traveling along this graph from left to right, oh, I'm not getting my color. There we go. When I hit -1, there is nothing there. So what we have to do is represent that. And we do it kind of in an exaggerated way. We draw a hole there. Now, why is the hole there? Well, actually, the hole should be at, let's see. No, that's right, -1, 1. This behaves like x plus 2 everywhere. So if I put -1 in here, -1 plus 2 would be 1. So at -1, 1, I should have my hole. And then the graph continues on. We exaggerate the graph this way with this big hole just to show that there's no value here. So again, we're looking at this just like we did in the last one. As I approach from the left, this is approaching the value of 1, the y value. As x approaches -1 from the left, the y value approaches +1, but it doesn't ever hit it. As x approaches -1 from the right, the y value approaches 1, but never hits it. So there's just this gap, and it's a very tough gap to look at. If we were to look on a graphing calculator and zoom in tight enough, I mean, down to like probably thousandths of a unit on each side of this point, you'll see that your calculator actually even show a gap there, all right? But that's what we call a point discontinuity, when the value doesn't exist there, but it does infinitely close in each direction. All right. If you notice, all of these have that kind of characteristic. If I look at it coming from the left and I look at the value, the function kind of behavior as it approaches from the right, they're approaching different values in different ways. This one approaches -infinity from the left. This one approaches +infinity from the right, causing an infinite discontinuity. They never meet. All right. Even if they were both approaching +infinity, there's still that gap in the middle. Here, from the left, it's approaching 1. From the right, the value of the function is approaching, again, when I say the value of the function, I'm talking about the y. As I approach, the x value approaches 0. So as I'm traveling down this graph from the right, the y value is approaching 0. From the left, it's approaching 1. Different values, we get a jump discontinuity. Here, from the left, it's approaching 1. From the right, it's approaching 1. So now they're approaching the same value, but at 1, they don't exist, or at -1, I'm sorry. There's no value, -1, 1 does not exist. So when they approach from the left and the right, but they don't exist there, we still have a hole. All right. So again, this is how we kind of look at these things. How does it approach from the left? How does it approach from the right? And that leads to how we're going to actually deal with these discontinuities. Besides, I never wrote down, I'm sorry, we have a hole or a point discontinuity at x equals -1. All right. But what we're going to do with these, how are we going to work with this? We are going to do something called a continuity test. We are going to be asked to decide, is a function continuous at a point? We're going to investigate a single point in a graph. So continuity test at a point is something we need to know. And when I say at a point, I meant point at any point C. All right, I should have done that this way. At a point, say C, for a function f of x. All right, so this is what we're going to do. We're going to develop this test. If we have some function f of x and we're investigating at point C, how do we do it? There's 3 steps. You got to do all 3 steps. Unless any one of them fails, then you can stop. All right, first, always the first step. And I would strongly suggest when you do these, you just write down number 1 and circle it so we can see. This is your first thing you're doing. We need to see that f of c exists. All right, so if I'm looking at this function, I'm investigating at x equals 0, the first thing I'm going to say is there a value at 0? And I would have to say no. So it would fail the first test. F of x equals 1 over x would fail immediately, and I just write fail and be done. This one would have a value. F of c does, if I was investigating at x equals 0, f of 0 is 0. It has a value for this. So it would pass the first test. This one, if I was looking at -1, this would fail the first test. All right. So different things can fail in different ways. So f of c exists. That's the first thing we have to check. And all we have to do to pass this test is write f of whatever value we have equals some value. All right. And I'm going to give you examples of that in a minute. The next thing we need, that the value, I'm going to write out the words, and then I'm going to show you the notation we're going to use. The value of f of x approaches or you know what? I don't want to put that many. I want to make it as succinct as possible. Let's just say, let's go here. All right, let's do it this way. I'm going to change what I have written down here. F of x approaches a single value, or you could say the same value. From the left and the right. All right, so how do we note this, that it works? Well, what you're going to talk about is the limit. We write limit like this, all right, just lim. In math, that's the abbreviation for limit. And what we're going to say as a subscript, it's going to be written below, is as x approaches that value, whatever that c is, of our function f of x equals something. If it approaches a single value from the left and the right, then that limit will be whatever y value that is. So the limit as x approaches some c value of f of x will be this y value. All right, it'll approach the same value from left and right. If it passes this, we go on. And I'm going to get into this more. I want you to know this is what we're going to expect to see. You don't have to write this, the words, but I want to see this. All right. This is important notation you're going to carry forward into calculus. So it is going to be something I want you to get familiar with right now. All right. So we have this. If these two things, if f of c exists, remember we would say f of c equals some value. And if the limit exists, it's going to be a single value, right? I didn't write value here. I'm sorry. I just looked up there and saw that. All right. These are both single values we're saying that we have. Well, if the value from this one if 1, that value equals 2, then we have continuity. All right, if they don't equal one another, where could that happen? Well, let's look back. Because here we're saying f of c exists, and then they approach the same value from left and right. There was one of these. You remember this one failed the first, or where is it? This one failed the first test. This one passed the first test, but it would fail the second test because as we approach from the left, we were approaching 1. As we approach from the right, we were approaching 0 for the function value. So a limit did not exist here. So we would just say the limit does not exist. All right. Again, important point here. So this would fail the second test and we'd be done. All right. So how do we use this continuity test? Well, this is what our problems are going to look like. As we do this, it's going to tell you, it's going to ask you, determine whether each function is continuous. I'm just going to abbreviate that, at the given x value. And it's going to tell you, justify your answer using the continuity test. All right, so it'll give you something like this. Y equals, we're just going to consider their f of x. Y equals 2 over 3x squared, and then it's going to say x equals -1. So is this continuous? What I would do just to get a feel for this, if they're asking you about something being continuous, I would go to my graphing calculator and turn it on, of course, first, and then go to y equals. And I want to clear that out. I'm going to put this function in, 2 divided by, in parentheses, you got to make sure you have parentheses around this bottom part, 3x squared, and close the parentheses. And I'm going to do just a standard graph with this. That is 6. And I want to see the graph. Now, if I look at this, my first impression is this has a discontinuity, but it looks like it's at 0. If I zoom in a little bit, let's zoom in. So let's go to 2. Let's zoom in. We're looking at x equals -1. So I'm going to move over that way a little bit and zoom in, hit enter. At -1, there's definitely, I think, well, we know at x equals 0, this thing is not defined, right? But it's telling us to investigate at x equals -1. At x equals -1, it would appear we have a value. Let's just double check. Let's look at the table. At -1, it does have a value. At -1, it's 2/3. So if we look at this, it looks like it's continuous. So I'm just going to say yes right off the bat, just because it looks like it's continuous. Now it's saying justify your answer. So first thing I have to do is say that f of -1, the function value at -1, is equal to what? Well, we just found out if I plug in -1 here, what do I get? I get 2/3. So it passes that test. The second thing, does it appear that our graph, again, if I go back to my graph, does it appear as I approach from the left and I approach from the, approach from the left and I approach from the right, that it's approaching the same value? If you doubt it, you can punch in values. You can do second calc, let's say -1.1. Whoops. Didn't get what I wanted, -1.1. All right, so if we do that and hit enter, it tells me there's a value there, right? If I say, and it looks like it's at 0.55, and then if I do it again, second calc value, and I do -1.01, even closer, right? And hit enter. It's at or it's at 0.65, getting closer and closer to that 2/3 value, right? And I could do the same thing checking from the right, but generally speaking, I look at this and just kind of look at it and say it appears it approaches it from both sides. So in that case, it does have a limit. What is that limit? Well, it's the value, isn't it? What is this approaching from each side? It's approaching 2/3. It's going towards that. So I write the limit as x approaches my value I'm investigating, -1 of f of x equals, it looks like it's approaching 2/3. So I'm going to write down 2/3. All right. And finally, so it's passed both these tests. It has a limit. It has a value. The last thing is, are these the same number? Absolutely. So I would just write that f of -1 equals, and I should have mentioned that checks, f of -1 equals the limit as x approaches -1 of f of x. And I'm done with that one. I've made my statement that it is continuous there, and I've proven it by saying that there is a value there, that it approaches that value from left and right, or approaches a value from left and right, and those two values are the same. All right, let's do another one. All right. So now we have, let's see. Let's do this one. Whoops. Started drawing there without meaning to. Sorry. Let's do the same directions for y equals x minus 2 over x plus 4. And they want us to investigate at x equals -4. So again, if you want to, you can graph this. All right, if I do graph this, y equals, let me clear that out. This is parentheses x minus 2 close divided by, in parentheses, x plus 4 and close that. And let's do a zoom standard, zoom 6, whoops, 6, sorry. And we get this. Oh, let's see, at x equals -4, I'm looking right here. That looks like we might have an infinite discontinuity, right? That's what it appears. It looks like it's an infinite discontinuity. I'm going to say no, but I've got to prove that. So I got to go through my test. My test, the first thing I have to say is f of x, f of -4 in our case, is equal to what? If I put -4 in here, I get -6 over 0, which is undefined. So this, and I've proven that it is not continuous there, because if it doesn't have a value there, it can't be continuous. And if you doubt whether it has a value at -4, you can always go back to here. And again, if we go to our table at -4, let's scroll up a little bit, we get an error, don't we? It's not there. So again, you're going to have to go through these, and you're going to see some different ways of dealing with this idea of a continuity. That's what we're going to ask you to do, is work with this continuity test to show these. Try your best with it. I know when you first start, this idea of a limit as x approaches a value of a function is difficult to understand, but I want you to give it a shot. I'm going to do one more for you, and then we're going to move on to end behavior. All right, let's do this one. Y equals x squared plus x plus 4 over 2 at x equals 1. All right. Again, if I look at this, I could graph this, and just to save us some time, it looks like it's continuous to me. But so I'm going to start out saying yes. It does look, when I graph this, like it is continuous. It looks like it flows straight across, like it doesn't have any place that we worry about. There's no infinite discontinuity I can see. There's no gaps in it, no jumps. So I'm just going to say yes. Now I got to prove it. And you could do the reverse. You could go through the proof first and then decide yes or no. That normally is the way I've taught it. But last year I started working with people, and they wanted to look at it on their calculator first. So I thought, if students want to do that, let's approach it that way. So let's do the proof now. F of, well, not x, f of 1, we know our x, f of 1 is equal to 1 plus 1 plus 4 over 2 which is 6 over 2, which is 3. It passes. It's got a value. The second thing, the limit, and I can write this out before I even do it, as x approaches 1 of our function f of x is what? Well, this is where I'm going to need to make sure that I can see it. So let's go to y equals and clear this out. And let's put this in here. Again, if you didn't do it at first, I generally do it at this step. And so let's say x squared plus x plus 4, and then divided by, need to put parentheses around the 2. All right, so let's just do a zoom standard on this. And when I look at this thing at 1, and if you want, you could zoom in. If I do zoom and I decide to zoom in at what looks like the 1 value is up there. Whoa, lost my graph. I think I went off it for a minute. All right, so if I do this, and let's just make this a little bigger. Oh, it doesn't want to be over there. All right, so if we do this and I just hit enter, and I look at it as we approach from the left towards the value of 1, and you could even do a trace if you want. This is another thing I've seen students do. If I look at it from starting from, this is x equals 1.48, so I'm starting from the right, and I travel towards 1 in the x values, it looks like I don't have any jumps or gaps or anything of that sort. It approaches, again, if I look from the left, I'm below 1, approaching from the left, it looks like it's approaching the value of 3, doesn't it? If you look at the y values, as I get closer to 1, it gets closer to 3. So it would appear that our limit as x approaches 1 is 3 as well. And again, we can say then that f of 1 equals the limit as, or of f of x as x approaches 1. And this would pass. So we're good. All right. Again, you're going to get a variety of these examples. We'll go through any problems you have tomorrow, but please try to follow that 1, 2, 3 approach. All right. The last thing we have to cover, and we'll do this kind of quickly, kind of I say, because I don't want to do it fast just for the sake of doing it fast. End behavior. With end behavior, we're talking about a function. I mentioned before, we talk about things moving left to right. So from negative infinity to positive infinity. What we want to know is what's happening to a graph as it approaches negative infinity or positive infinity. So when we look at something like y equals x squared with that shape, what we're going to do is, it's a real simple script, and I want you to keep it this simple. If they tell you to describe the end behavior, describe the end behavior of a graph. All right, if they ask for this, if they ask to describe it, you're going to just do 2 things. And I do it a little bit different than the book because I think it makes more sense. I say as x approaches negative infinity, because we're going to look at as x is going this way. All right, we want to know, there's a comma, f of x. And I've also seen y used here, but you could say, and I don't care which one you use, f of x or y, approaches. These arrows just mean approaches. All right. And we want to fill in this blank. This is just an empty box. And then we're going to say as x approaches positive infinity, f of x or y approaches what? All right. So if I look at this graph of, this is just y equals x squared. All right. And I want to describe the end behavior of this. I would do it this way. I would say as x approaches negative infinity, just using my script, f of x, or in this case, if I wanted to say y, what is the y approach? As x is going this way, y is going towards, it just keeps getting bigger and bigger, goes towards positive infinity. So I just write positive infinity. As x approaches positive infinity, f of x approaches. So as x approaches positive infinity, what does y approach? approaches positive infinity as well. So I just do that, and I'm done describing it. That's all I need for my answer. So you just need to kind of learn this script and work with that. So if we had something, another one that we wanted to do, let's say we do y equals, let's do something we wouldn't know what it would look like. Let's say, let's do, we'll do this one. 5x cubed plus x squared minus x plus 4. You guys know what that looks like? I don't. So what do? If I don't know, I'm going to go to my calculator. I'm going to go to my y equals. I'm going to clear it out. And I'm going to do this one in it. I'm going to put this in here. 5x raised to the third plus x squared. Where's my squared key? There it is. Minus x plus 4. By the way, if you're wondering where I got this, see the Wabbit EMU up here? You can put this on your phone, and it's awesome. It's a free app called wabbit.emu or Wabbit EMU. If you look it up in your, whether it's Apple or Android, you can get just like this on your phone. It's awesome. I think I mentioned in class to a few of you, it's a great tool to have if you don't have a graphing calculator with you. Your phone can be one. So I'm going to graph this. Again, I'm going to go back to, I always hit zoom 6 because it gives me just my 10 by 10 graph, 10 x's each way. All right, so if I want to narrow this in a little bit more x-wise, I'm going to go from -5 instead to 5 and zoom this graph in a little bit so I can see it better. All right, so what looks like it's happening? It looks like as x approaches negative infinity, so let's go back to this. All right, I'm going to get away from this for a minute and say, all right, I want to describe the end behavior as x approaches. And I often, before I even graph it, sometimes I'll just write this. And that way I just have to fill in the blank as I see it. All right. So now I look back at this one again. And where's my Wabbit? There it is. As I look at this, all right, as x approaches, x is going this way. What's happening to y? Y is going down, down, down forever. So as x approaches negative infinity, the f of x, or y, is approaching negative infinity. In the same way, if I look at my Wabbit, as x approaches positive infinity, what's happening? It's going up forever. And you can trace this if you want, or look at the table just to make yourself more sure of that. But generally speaking, what you see is what you get on that calculator. This is approaching positive infinity, and I'm done describing it. All right, one last one. Let's do, let's say f of x equals 1 over x. All right, f of x equals 1 over x. Well, we know what that looks like, but let's put it on our calculator just for fun. Let's go to y equals, clear, and this is going to be 1 divided by x. And we'll do a zoom 6 on it again and graph this thing. So we get this, and we know this graph pretty well. And we're not looking at anything here but end behavior right now. So don't worry about discontinuities. All we're asking is you need to fill in the blanks in this statement. As x approaches negative infinity, f of x approaches what? And as x approaches positive infinity, f of x approaches y. So again, I'm going to look at this and think of what's happening. If I go to trace this and I start making x, all right, this is x at negative 0.2. If I start making x go further and further left, what are the y values getting closer and closer and closer to? They are getting closer and closer and closer to, they're getting smaller and smaller, right? In the negative sense, they're getting smaller and smaller this way until they approach 0. So they don't hit it, but they approach 0 as x approaches negative infinity. Well, what happens if I go the other way? If I trace this way, we know I trace and I trace and I trace. Now I'm going as x approaches positive infinity. This value is getting smaller and smaller and smaller, approaching 0. So again, we're just looking at the behavior. Where is it going towards? It's approaching 0 and 0. All right. So that's describing end behavior. Probably one of the easier things we did this year after you get through the concept. Now you got to be able to get your head around what we're talking about. I know when I say something's easy, I always worry someone says, oh, but it's not for me. I get that, but we'll help you make it easy. All right. So that goes hand in hand with the next thing we're going to look at. The next thing we're going to look at is being able to describe the intervals where something is increasing or decreasing. So the next thing they're going to ask you on these, we'll do the same questions. Determine the intervals for which each function is increasing or decreasing. All right, so now we're going to have to go back to our graphs. All right, and this isn't as bad as it sounds. If we go to that graph of x cubed or 5x cubed, I got to go back and put it back in. Sorry. Let's clear. That didn't take that long. 5x raised to the third plus x squared minus x plus 4. And I think we did our window from -5 to 5. And let's do the y's that way too. Now let's do the y's from -5 to 10. And let's graph this. I just try to pick where I can see it well for a window. All right, so we have, it says describe the intervals where it's increasing or decreasing. This is where we go back to tracing left to right. Like I said, when we describe the behavior and things of that sort, we often go back to this. As I'm traveling along this graph, what's happening to the y values here? Are they increasing or decreasing? They're increasing, right? And then they hit a point here where for briefly they're decreasing and then they're increasing again. If you doubt that, you can zoom in on this. We can get our window between say 0 and or maybe 1 and 7. Not that window between say 1 and I'll just leave it 1 to 5 and graph it. Oh, I didn't want that. I'm sorry, I did the wrong ones. Window between, I still want window for the x's. I wanted these. All right, so let's go down there. Sorry. 1 to, I'll just leave it 1 to 10 and graph it. So again, it's increasing, slowly decreasing there for just a short point and then increasing again. So how do I describe this? All right, the way we're going to do this is with what's called interval notation. We know we're starting at -infinity. So what we're going to do is we're going to use a parenthesis. So I'm going to say increase. I'm going to make two headings, increasing and decreasing. So my increasing heading is the first one because as we saw in our graph, it's increasing first. And it's increasing starting at -infinity. So I put that in as my starting point. I put a parenthesis here because we can never reach -infinity. All right, and it would be a bracket if we could, if it includes the endpoint. We're not including the endpoint, so we put that. All right, and this is easier than writing. I'll show you what this means in another way. Then we're going how far? Well, we're going to go up to wherever this turns around. So we got to find that point. That's a maximum value, isn't it? A local maximum is what we call it. So we've got to find where that point is a local maximum. So we can do that with our calculator. If we go to second and calc, we can see that we can ask for a maximum. So we can ask for it to find a maximum. The way we do this is it says left boundary. What it's saying is it wants to know, go left of that maximum. Right now it looks like it's right of the maximum. So I'm going to move this cursor left, anywhere left, it doesn't matter. Just left of that high point and hit enter. And then it asks you right boundary. All it's asking is where to look for this maximum. It's going to do a calculus process for us and it's going to find this maximum. So now I go over the hill and hit enter again. And I just do that using my left and right keys. And now it says guess. I don't want to guess, just hit enter and it'll tell you the maximum. the maximum happens at x equals negative 0.33 repeating. So I want you to go to at least that one decimal past. I know that's what your book does, so we'll be okay with that right now. In calculus, they're going to want you to go to 3 decimals, but we'll say it goes to negative 0.3. So looking at this from x equals negative infinity all the way up to here, it's increasing. Then what happens? From that point, because that's the maximum, it starts to fall. So what I do is I go to my decreasing side, because now it's going to be decreasing. The y values are going to be decreasing momentarily. So I put negative 0.3 as my starting point for the next decreasing interval. Again, I started with a parenthesis. Now what do I need to do? I need to find the minimum. If I find that minimum, I can go back and use that as the endpoint of this decreasing interval. So again, I'm going to go to second calc, and I'm going to ask for a minimum this time, which is number 3. And when I do that, it's asking me again, where do I look? So I got to go left of this kind of valley. I am already left of the valley. So I can just stay right there or move maybe a little bit closer, but don't go past it. All right, go to the left of the valley, hit enter. Then it asks for a right boundary. So I'm going to go right of the valley. Remember, the minimums look like valleys, maximums look like the hills, right? So I'm right of it now. I hit enter again to let it know. See how it's putting these 2 little arrows up here? It's saying I'm going to look between these 2 for that minimum. So then hit enter. You don't have to guess. And it'll tell you the minimum happens at 2. Now, it told me 2.00000034. It had all those zeros in there and then 34. It actually is at 2. And the reason I say that is your calculator is doing a calculus process where it's trying to find that minimum. So it's Newton's method of finding that minimum. It only does a few iterations. With Newton's method, the more iterations you do, the more accurate it becomes. So what it does, it gets as close as it can. You have to be the human and interpret this and say, that happens at 2. All right, this means 2. So I put 2 as my decreasing endpoint. Well, then what happens to my graph? From that point, it's increasing forever. So I'm going to go to my increasing interval, start a new interval that starts at 2, the x value, for the x value, and it goes on forever to positive infinity. And I've completed all my increasing and decreasing intervals. And that's all I have to do. All right. So how would we do that for, this is the answer, by the way, when it says decrease or determine the intervals for which the function is increasing or decreasing. This is how we do it. So how could we do it for this one, 1 over x? All right, let's go back to that graph. I'm going to clear this out again, y equals clear, and let's do 1 divided by x. And let's do zoom 6 again and see what this looks like. Oh, did I get my graph in there? Let's do second quit. Yeah, there's one quick way to do that. All right, y equals 1 over x and window. All right, so let's graph it. There we go. All right, so we know what this looks like. What's happening here? As I start at negative infinity and travel along this graph, what's happening to the x values? I should say, as the x values go left to right, what's happening with this function? It's decreasing all the way until we hit 0. At 0, it jumps. And what happens again? It's decreasing again. So this graph is technically decreasing everywhere, but it has a gap at 0. So if I want to describe this one, again, I'm going to go back, and I always do this. I always start by saying I've got an increasing set of intervals and decreasing set of intervals. As I just mentioned in here, we start at negative infinity, close to 0, right, the y value, and then those values decrease infinitely as they approach 0. So my first decreasing interval is going to, again, start at, this time it's decreasing, starting at negative infinity. I put a comma, and where is it going towards? It stops decreasing as it approaches 0. It never gets to 0, but it keeps decreasing until it's infinitely close to it. That's why we have a parenthesis here, not a bracket. It's not going to reach 0 adding the x value, but it's going to get really close to it, and it's going to keep decreasing. Then what happens? Then, after we get past 0, coming at 0 from the other side, it starts to decrease again. So it's another decreasing interval starting at 0, not including 0. Again, I put a parenthesis, and going all the way to positive infinity, it's decreasing again. There are none of these. So I put none, or NA, not applicable. There are no increasing intervals. So again, we're going to look at intervals where things are increasing or decreasing just by what happens as we travel along left to right. So that's one of the key things. When you're deciding these, you're moving left to right. And you want to see, are the Y values increasing or decreasing? And then we express these intervals as X values, right? We express the X values that they're between. Parentheses for those endpoints of these intervals. All right? That's it. I know that was a long one. Thank you for sticking around this long. Probably had to do it in 2 or 3 sessions. If you're like what I just talked to a student said, I just do 10 or 20 minutes at a time. So if that's the case, I hope you enjoyed this. I hope you got something out of it, and go try the practice and do your best with it. And I know you're going to get a little frustrated. Everyone does during this at some point in here. There was a lot of different things. Do your best with it. Ask a lot of questions tomorrow. It'll become a lot clearer. You'll get a second chance at it. All right. So without further ado, have a great day. And I'll see you back here when we go on to 3-6.